Hey, so we've discussed the unique pointer before, so in this lecture I want to introduce the shared pointer. You can see an example for the syntax at the top of the slide. Now in some ways this is going to be similar to the unique pointer, but the ownership can be shared, so you can have one or more owners. In other words, the heap object can be managed or owned by multiple shared pointer objects. Now if you remember, with the unique pointer, the copy constructor and the copy assignment operator was explicitly deleted, but that is not the case for the shared pointer. The copy constructor and the copy assignment operator is available for the shared pointer. Since multiple pointer objects can manage, so in other words own, a heap object, how to deal with the deallocation of that managed heap object? Because we don't want dangling pointers and we don't want crashes, right? If a heap object has multiple owners, then we don't want one of those owners to go and deallocate that heap object when another one may still reference that. So shared pointers use a reference counter to keep track of the number of shared pointer instances that manage a specific heap object. And with every new owner, the reference count gets incremented. In other words, when you use a copy constructor or a copy assignment operator, and that heap object now has another owner, then of course you want to increment that reference count or use count. And then also when an owner gets destroyed or gives up ownership, then the reference count gets decremented. We can use the useCount member function to check the reference count. And with the shared pointer, the heap object does not get deallocated until all owners have gone out of scope or have given up ownership, and the reference count will be 0 in that case. When the last owner gets destroyed or gives up ownership, it's going to deallocate the heap object through the pointer that it manages. When a smart pointer instance is reassigned or reset, it's going to stop owning the heap object, and again the reference count is going to get decremented. As with the unique pointer, the shared pointer has the overloaded dereference operator and the member selection or arrow operator for familiar workflow. And then of course we also have to include the memory file for the shared pointer. In this example, I'm going to include the memory file again for the smart pointers, and then have the class entity again, just some abstract entity class with a constructor with a default argument. And the main reason for using this entity class again is that we have a destructor, so we have a destructor printout, and then we also have some toString and a setMember function, and of course the private member right here, which is an integer. Alright, in the main function we can declare and initialize a shared pointer. Just to keep it simple, I'll use SPTR here for shared pointer. We have a shared pointer which is going to manage this type, an integer, and on the heap we allocate a new integer here, and I pass in 55 for the initialization of that integer. Then I'm going to do console output. I'm going to dereference, so we have the overloaded dereference operator for the smart pointer as well. And if I build around that, we should get 55 printed out. And that's what we get. Of course I have this entity class up here because when it gets destroyed, we're going to get this printout. So I'm going to use that. Then I can use the member selection or the arrow operator to access the toString function, which again is a member function of the entity class. We can build around that. And now we get 55, end of program. And now when we reach the closing curly brace of the main function, we get entity destruct invoked. Member was 55. Again, similar to the unique pointer, the shared pointer is going to manage the heap object for us. Once the shared pointer, so in this case SPTR, goes out of scope, which will in this example be once we reach the closing brace of the main function, SPTR, the shared pointer, is going to get destroyed, and that is going to deallocate the heap object automatically. Right, we don't have to worry about that, we don't have to do that explicitly, similar to with the unique pointer. I'll just do the statement here. I have the useCount member function, which I will invoke to basically get the reference count, or in other words how many objects are managing the heap object, or in other words how many objects member pointers are pointing to the heap object. And as we can see, the SPTR useCount is 1, so only one object is managing that heap object at the moment. Now let's do something else. I'll go and rename that to SPTR1. And then I'll create another smart pointer. And as I mentioned, the copy constructor is available for the shared pointer. Both of the shared pointer objects, SPTR1 and SPTR2, now manage the heap object that we allocate right here. I do SPTR1.toString, and the use count for both of those should now actually be 2. I'll just copy this right here. So the use count for both of those objects, SPTR1 and 2, should now be 2. Build around that. And you'll see that is what we get. But we only get one destructor invoked. we don't get it invoked twice. Of course, we only have one object on the heap, not two. Both of those will now manage the single object, and when the final one goes out of scope, it will delete, or in other words, deallocate the object on the heap. For an exercise, I'd like you to test the reset member function for the shared pointer, and then document your findings on that. In the previous example, we had these two shared pointers, which are just called shared pointer 1 and shared pointer 2, both of them managing the same heap object. Now, for example, one thing that we can test is what happens if we reset the shared pointer 1 object. Does it allocate the heap object or not? It shouldn't, right, because shared pointer 2 also references that heap object. Also, following the reset member function invocation, what will the use count be? Okay, you can do a check as we have in the previous example. Again, if we do reset on the object shared pointer 1 but not on the object shared pointer 2, what will the use count be on each one of those? Another thing you can test is if we can use the reset member function to set the shared pointer to manage a different heap object as we could with the unique pointer. So go ahead, pause the video, play around with the reset member function, note your observations, and continue the video following that. Before moving on, let's look at a few examples of shared pointers. So I have a few illustrations here. I have the stack and the heap, and in the main function, on the stack I have instantiated a shared pointer. I call that shared pointer A. Currently its member pointer is basically null pointer, it's not pointing to anything on the heap. In other words, shared pointer A does not manage a heap object at the moment, and so the reference or use count will be 0. Now let's say we allocate an object on the heap for that shared pointer A to manage. You can see on the heap we have an object now, and the member pointer of shared pointer A is pointing to that. So shared pointer A is managing that heap object, and so the use count or reference count will now be 1. Okay, that heap object has one owner. Now maybe we have a statement like this. We do shared pointer some type, right? We construct shared pointer B as a copy, so we're going to use the copy constructor and we pass in shared pointer A. That again is valid with shared pointer, so we have the shared pointer B now on the stack. Both shared pointer A and shared pointer B manage that heap object now, so the use count will be 2. Next, let's look at the reset function for the shared pointer. As an example, we have this statement at the top, shared pointer B.reset. In this example, we don't allocate a new heap object for shared pointer B to manage. So following the statement, the shared pointer B is not going to manage a heap object, and its member pointer will be set to null pointer. Also, you can see what happens to the use count or the reference count. The use count for shared pointer B will be set to 0 because it is not managing any heap objects, and for shared pointer A, the use count will be 1 because that heap object is managed by a single shared pointer. Next, what is going to happen when shared pointer A and shared pointer B goes out of scope, or in other words gets destroyed? Let's say we reach the closing curly brace of the main function, for example. Shared pointer B does not manage anything on the heap currently, so we can destroy that. When shared pointer A goes out of scope and gets destroyed, the heap object will get deallocated because the shared pointer A is the only object that is currently managing it. Now I would like to note that these illustrations were a simplification because there is more to the shared pointer than this. The shared pointer actually has two pointers, one to the managed heap object and another one to something called the control block, which is another heap object that keeps track of the reference count, but I'll talk about this in more detail in an upcoming lecture, that is once we've discussed the weak smart pointer. Okay, I'm back in Visual Studio. In the main function, I'll move things around a bit, so I'll move this line up, and this one I'll move down. I'll add these two statements within a compound statement or a code block, and you'll notice that Visual Studio automatically indented these two statements for us when I added the closing brace down here, so that's quite nice. Now remember with these statements, this one right here and this one right here, I do smart pointer 1 and smart pointer 2 use count, but those are basically going to be the same if they point to the same heap object, or in other words if they manage the same heap object. I'll just copy that statement and paste it down here. Maybe you can pause the video for a second and think about what the output is going to be when we build and run this program. Okay, if you think about it for a second, this is going to print out 1, right? Then we have another shared pointer here, shared pointer 2. We use the copy constructor and pass in sptr1. So within this compound statement, two shared pointers now manage the heap object. So this statement right here should print out 2 here with the useCount function. This here should print out 55, and then this here should print out 2. And then following that compound statement, of course, the shared pointer 2 is going to go out of scope. So this statement down here should print out 1 again, so we'll get 1, 2, and 1 for the use count. Let's just build and run that so you can see what I mean. We invoke the toString, so we get 55. Then we do the statement where we print this out, sptr1, we get a use count. So one shared point is now managing that heap object. Then we enter the compile statement or the code block. We get 55 printed out in the toString function. Then we get shared pointer 2 use count is 2. Following the compile statement, we get shared pointer use count is 1. we get one entity destruct invoked. That is when we reach the closing curly brace of the main function. And as I mentioned, these statements are basically going to be the same, alright? So you can actually just remove those. And you can also make them all the same. I'll use a 1 here because SPTR is going to be out of scope down here and up here, of course. So we'll just use SPTR 1 for each one of those statements and build and run. And we should get shared pointer use count is 1. That is before we reach the compound statement. Within the compound statement, of course, we have two objects, two shared pointers that manage that single heap object. So we get 2 here. Following the compound statement, the shared pointer 2 gets destroyed because it goes out of scope. It does not deallocate the entity heap object yet. And then following the compare statement, we get shared pointer use count is 1. Then we get end of program. Program execution will reach the closing curly brace of main. So we get entity destruct invoked. Because at this point, shared pointer 1 will go out of scope, and that is the only object that currently manages that entity heap object. Okay, the entity heap object will get deallocated. Again, within the compound statement, following this statement right here, we have two shared pointers, shared pointer 1 and shared pointer 2, that manage that heap object. Then we do this toString right here. Then we print this out. So within this statement, of course, the use count is going to be 2. Then program execution reaches the closing brace of this compound statement. Shared pointer 2 here will go out of scope. So the use count will get decremented. Only one object, SPTR, now manages the heap object, which we've allocated right here. And that is why in this statement we only get 1 printed out. Okay, I'll mix this example up a bit and I'll cut this out. SPTR will get initialized now to null pointer. Actually, I'll just remove these braces. Like that, so that is going to be initialized to null pointer. In other words, the pointer that it manages will get initialized to null pointer. Then I don't want to do this, of course, so I'm going to remove that. But I'll still do this statement. So the use count should be 0 right here. Then I'll actually allocate that heap object where we construct the shared pointer 2. So instead of using the copy constructor here, I'll allocate that entity, and then I'll just remove that comment. Then we can do toString if we want. To demonstrate that the copy assignment operator is available for the shared pointers, I can do this statement right here. I assign shared pointer 2 to shared pointer 1. Basically what this means is both of these shared pointers now manage this object on the heap. So this right here should print out 2, and then here this should print out 1. If you don't understand why, you may want to pause the video for a second and think about why that is. Okay, I'll build around that and we should get, as I mentioned, we will get 0 because that shared pointer 1 at that point did not manage any objects on the heap. Then we get the 55 from the toString. Then we get shared pointer use count is 2, that is within the compound statement. That is following the instantiation of shared pointer 2 and the heap allocation of an entity object that it will manage. And then of course we also do the assignment of shared pointer 2 right here of shared pointer 2. We assign shared pointer 2 to shared pointer 1. And then of course again when we reach the closing curly brace of this compound statement, shared pointer 2 is going to go out of scope, but it will not deallocate the heap object just because we have declared it within the scope. That heap object is now managed by both this one and the shared pointer 1 as well. So both shared pointer 1 and shared pointer 2. So when we go out of the scope, out of this compound statement, shared pointer 1 still manages that heap object, and of course that only goes out of scope when program execution reaches the closing brace of the main function. So this statement right here will print out 1 for the use count, as we can see right here. So we get 2 within the compound statement and 1 following the compound statement. Program execution reaches the closing curly brace of main and we get entity destruct invoked. Okay, so we deallocate that heap object and free up that memory. Let's continue with our example in main, so I'll delete the statement right here. So within the compound statement, what we'll do is, we'll go and construct shared pointer 2. Then we'll do the statement, we'll assign shared pointer 2 to shared pointer 1, and then we'll do shared pointer 1.toString. Okay, just to illustrate to you that the assignment operator works for that is the copy assignment operator for the shared pointer. Okay, so we'll do that toString, and that should print out 55, and then we'll do shared pointer 1 use count, and we'll print that out. Okay, I'll have these two printouts where I print out the use count for shared pointer 1 and for shared pointer 2. Now right before we do the shared pointer 2, actually before we do that, let's just build a run here so we can see what we get. Within the compound statement we get 55 printed out. That is where we invoke the entity toString member function. Then we get shared pointer 1 use count is 2, and shared pointer 2 use count will be 2 as well. Both of those manage the same heap object. Following the compound statement, shared pointer use count will be 1. Okay, that is shared pointer 1. The use count for that will be 1, because again, shared pointer 2 goes out of scope, right? Now between these two statements, what I'll do is, I'll invoke the reset shared pointer member function. And you can think for a second what's going to happen with our printouts. Okay, build and run that. Now you can see in the compound statement, shadePointer1 use count is 2. That is right here with this statement right here before we do the reset. Then we do the reset and then we do this printout. So we do shadePointer2 use count will be 0. That is because currently shadePointer2 does not manage any heap objects. Okay, so that will return 0. Now remember we use that reset member function. So that is going to decrement the use count. That is of the managed heap object because the shadePointer2 no longer manages that heap object. So that will be 1. And actually I can just copy this statement here as well. Paste it down here. And if this is confusing, you can comment this out. Or you can add extra printouts within the code block to make sure that you understand, okay, this is happening within the code block. Or you can step through this using the debugger, of course. Build and run that again. So remember with this, we do shadePointer1 use count, then we do reset, then we do shadePointer1 use count again, right? So shadePointer1 use count, we get 2, because shadePointer1 and shadePointer2 at that point manages that heap object. Again, following this printout, we do reset. So shadePointer1 use count is now 1. ShadePointer2 use count will be 0. Also notice with the reset member function in that compound statement, that does not deallocate the heap object. The heap object only gets deallocated down here where we have entity destruct invoked. That is when we reach the closing curly brace of the main function. That is because shadePointer1 is outside of this code block. And as with the unique pointer, we can check for null pointer with these shared pointers. This should evaluate to true because shadePointer2 does not point to anything on the heap at the moment. Build and run that. And the check succeeds, we get null pointer printed out and the shadePointer2 use count will be 0. Also, before I continue the discussion on the reset member function, you can also do this. You can also set it to null pointer in this way and build and run that. And you can see the results are the same. We get null pointer printed out and shadePointer2 use count is 0, whereas shadePointer1 use count will stay 1 and the entity destructor will get invoked when the main function exits. But just for fun, let's say we do. Let's assign null pointer to shadePointer1 and build and run that. Following those statements, entity destructor gets invoked so that heap object gets deallocated, and then we get a null pointer printed out for shadePointer1, and then all of the use counts will be set to 0. Okay. We can also use the shadePointer's reset member function to basically replace the owned heap object. So this statement again is not going to deallocate the heap object because shadePointer1 also manages the heap object that we allocate right here. But what we are saying with this statement is we no longer want shadePointer2 to manage this object. Okay, we want it to own or manage its own object, this one right here. So what's going to happen if you think about this for a second? The statement is going to decrement the use count for the entity that's on the heap, this one right here. Following this reset member function invocation, this heap object will be owned only by shadePointer1. Okay, so this statement again is going to decrement the use count for that. But this printout here, shadePointer2 use count will be 1 now instead of 0 because the use count or number of owners for this heap object will be 1, in other words this instance right here. And of course that will be deallocated when we reach the closing curly brace here of the compound statement. And then following the main function, that is where we reach this closing curly brace, we will deallocate this entity right here. That will be managed by the shadePointer1. Build and run that. Okay, we get those 4 printouts in the compound statement. ShadePointer1 use count is 2, that is following the assignment. Then we get the reset function and ShadePointer1 use count will be 1 because the use count for that entity on the heap will be decremented. Then we get ShadePointer2 use count is 1 because that is now managing this entity object on the heap that stores 150 in its member. But of course you can see we get the entity destruct invoked because we reach the closing curly brace again here of this compound statement right here. And then following that we do these 2 printouts, the ShadePointer1 use count and then the end of the program. So this is what we get. We get ShadePointer1 use count is 1, end of the program, and then that entity on the heap that stores 55 in its member will get deallocated because ShadePointer1 goes out of scope. Okay, this pointer right here will go out of scope. So a bunch of demonstrations, but you can see this is really easy stuff. Next, as I've demonstrated with the unique pointer, we can also use a shared pointer to manage an existing heap object. Okay, so I'll use a raw pointer. I'll allocate that object on the heap right here and assign the address to that raw pointer. And then I'll use that raw pointer right here to initialize the shared pointer 1. I'll print out the use count, we'll get 1, and then we get entity destruct invoked following the end of the program. That is when we reach the closing curly brace of main. We get member was 55, that is correct. And as we can see, that shared pointer now manages the heap object that we allocated and where we store the address in the raw pointer. Okay, so this is one thing that you can do when you work with raw pointers, is you can have the unique pointer or a shared pointer manage the heap object. As I discussed before in the unique pointer lectures, it's important to avoid crashes. So for example, if I go and allocate that raw pointer using the delete operator explicitly like this, and we reach the closing curly brace of the main function, then of course we are going to get a crash because the shared pointer is now going to try and allocate that heap object. Let's just build and run that. And you see we get a crash. Okay, we get an assertion failed. We get entity destruct invoked before we get the end of the program. So we will get a crash. Alright, I'm just reiterating that when you want to use a unique pointer or a shared pointer to manage an existing heap object, okay, we pass in that raw pointer to initialize the shared pointer or the unique pointer. Then of course we want the smart pointer to handle the deallocation of that heap object and the management of that heap object. So you're not going to work with it any further, you're not going to deallocate it using the delete operator explicitly. For this next example, I've cleaned up the main function a bit, so I'll just go back down to that. I want to talk about the getMember function for the shared pointer. Now, similar to the getMember function for the unique pointer, the getMember function of the shared pointer is going to return the address of the heap object, otherwise it's going to return 0. For example, in this statement, we have shared pointer 1, hptr1, which is of type shared pointer and a passing entity, and now we can do something like this. Okay, so shared pointer 1 manages or owns a heap object. Is that going to be true or false? We're going to do a check for that. Instead of checking whether this returns 0, we are going to check for not 0. Because as I mentioned, this getMember function is going to return 0 when the shared pointer does not own a heap object. Let's just build and run that. So we get shared pointer 1 manages a heap object. That is going to be false. Right, we use the bool alpha stream manipulator to ensure that a boolean will display true or false instead of 1 or 0. Now, since the shared pointer 1 is going to own this entity on the heap, this expression should print out true. Build and run that. And you can see what I mean. Shared pointer 1 now manages a heap object that is going to be true. We get end of program and the entity destructor gets invoked. So a summary on some of the shared pointer member functions. We have the useCount member function that is going to return the number of shared pointer instances that own the owned heap object, or in other words, that own the heap object owned by this. This of course referring to the object on which we invoke the useCount function. Then we have the getMember function, which is going to return the address of the owned heap object. If the shared pointer instance does not own a heap object, get is going to return 0. Then we also have the resetMember function, which is going to deallocate or replace the owned heap object. Before it replaces the owned heap object, of course, it's going to decrement the reference count for the owned heap object. And if the reference count is 0, then the managed heap object is going to get deallocated. In my examples and in my summaries, I talk about the owned heap object or the managed heap object, but that is also sometimes referred to as the owned resource. I just prefer to use heap object instead of resource. In upcoming lectures, we'll continue the discussion on the shared pointer, but for now, I want to wrap this lecture up by talking about the makeSharedHelper function. If you remember, for the unique smart pointer, we have a makeUniqueHelper function. Now, similarly for the shared pointer, we have a makeSharedHelper function. Now, this makeShared function is going to construct and return a shared pointer that owns an object of the specified type, in this case entity, but of course that can be integer or something else. So again, within the angle brackets, we specify the type. That is the type of the heap object that the shared pointer will own. And then between the parentheses, we specify 0 or more arguments, and the function is going to use that to infer which constructor to invoke. Again, based on those arguments that you specify. And we get 150 printed out, end of program, and then we get the entity destructor is invoked. Both of those shared pointers manage their own heap object now. Of course, we can use the auto keyword for type deduction. And you will see this will work fine if I build a run. This will work fine, we get those two printouts and then we get those two destructors invoked. And the compiler will deduce these types correctly. Control K, Control I, and you can see we have the correct type. Later in the lesson I will discuss the make shared again. I'll do a summary on the make shared. But just to summarize, the make shared is going to be more efficient than this sort of syntax, because basically a shared pointer has two pointers, one to point to the heap object and another one to point to something called the control block. Now the control block is actually what is going to keep track of how many references, or in other words how many shared pointers reference that heap object. The control block is also a dynamically allocated object on the heap which will deallocate itself actually when the reference count reaches 0. But again, that also keeps track of the reference count, not the shared pointer object itself. So again, this may be confusing right now, but in an upcoming lecture I'll illustrate this to you and I'll summarize that for you. But basically what it boils down to is this syntax right here, where we explicitly use the new operator. That is going to be less efficient because you have to do two allocations, one for the heap object and one for the control block, whereas this statement right here, where we use make shared, that function basically does only one allocation on the heap. So there is some optimization with that, and it's also safer to use make shared. If heap allocation should fail for some reason, then this make shared is going to be more safe. The syntax is going to be less safe and you may actually leak some memory. So again, there's a lot going on here, but basically what it boils down to is use make shared instead of this older syntax here. Okay, here's an exercise for you to wrap up this lecture. Go ahead and experiment with shared pointers as formal parameters. We had a lecture on unique pointers as formal parameters. This lecture is getting a bit long, so in the next lecture I'll talk about shared pointers as formal parameters, but I want you to experiment with that before we get to the next lecture. So go ahead and experiment with pass by value and pass by reference, and in each case you want to think about how the function invocation is going to affect the use count. So in other words, how many shared pointers reference a particular heap object. Okay, for now that is going to wrap up this lecture on the shared pointer. We will continue the discussion on the shared pointer in upcoming lectures.